Hello everyone. Today we will be discussing results related to algebra of convergent sequences. What do I mean by that? So, if I have two sequences xn and yn which are convergent, then what can we say about their addition or their product or their division? That's what we will talk about. Okay. So, let me state the result first. Suppose we have two convergent sequences xn and yn. Suppose we have two convergent sequences xn and yn with xn converging to x and yn converging to y. Then xn plus yn converges to x plus y, xn into yn converges to x into y, alpha xn converges to alpha x, and xn by yn converges to x by y, provided no yn is 0 and y is also not 0. Provided yn is not equal to 0 and y is also not equal to 0. We have to prove these four results, and we will be using the properties of sequences that we have studied so far, and of course the definition of a convergent sequence. So what do we know from the definition? That if I want to prove that a sequence converges to a given point, then we have to show that given any epsilon greater than 0, there exists some n naught after which all the terms of that sequence are within the epsilon neighborhood, right? So let me do some background thinking first. I want to show xn plus yn converges to x plus y. Okay, so we will start with this part A. Now, what it means? It means that what I have to show is given epsilon greater than 0, there exists n naught in n such that mod of xn plus yn minus x plus y, this should be less than epsilon for every n greater than or equal to n naught. This is what we have to show. So what can we do about this? This could be rewritten as xn minus x plus yn minus y, and then triangle inequality gives me a way to separate this. And further, I know that xn converges to x, yn converges to y. So if I can make this difference, of course in modulus, smaller than epsilon by 2, and if I can make this difference in modulus also smaller than epsilon by 2, then their addition will be less than epsilon. Okay, so that is what we will do. As I said, this was background thinking. Now let us write the formal proof. Okay, so given epsilon greater than 0, there exists n1 in n such that mod of xn minus x is less than epsilon by 2 for every n greater than or equal to n1. Okay, this is first statement. With this same epsilon, so for the same epsilon greater than 0, there exists n2 in n such that mod of yn minus y is less than epsilon by 2 for every n greater than or equal to n2. Now ideally I want both these to hold. I want mod xn minus x also to be less than epsilon by 2, and I want mod yn minus y also to be less than epsilon by 2. So I want to talk about n which is larger than both n1 and n2. Okay, therefore we define n naught as maximum of n1 comma n2. As a result, for every n greater than or equal to n naught, both these will hold. Mod xn minus x will be less than epsilon by 2, and mod yn minus y will also be less than epsilon by 2. So we will write given epsilon greater than 0, Now I have this n naught, so what I know is I will start with this mod xn plus yn minus x plus y. This I will write as mod of xn minus x plus yn minus y, which by triangle inequality can be written as less than or equal to mod xn minus x plus mod yn minus y. And now I know that this first term is less than epsilon by 2 and second term is also less than epsilon by 2 for every n greater than or equal to n naught. Okay. Thus, what do I have? I have mod of xn plus yn minus x plus y is less than epsilon for every n greater than or equal to n naught. And that's what we wanted to prove. Therefore, we have proved that xn plus yn converges to x plus y. Okay. So this concludes our part A. Now before going to part B, let me go to part C because it's easier. Okay. So first let us try to prove part C. In part C, I have to show that if xn converges to x, then alpha xn converges to alpha x, where alpha is any real number. Okay. If alpha is 0, then my sequence becomes constant sequence. Okay. So if alpha is equal to 0, then alpha xn is simply 0 and it's a constant sequence, and of course it will converge to 0, which could be written as alpha x. So the result is true when alpha is equal to 0. Hence we have to consider only the case alpha not equal to 0. Okay. Now again let us try to think what I want to show. So we are again doing background thinking. What I want to show is mod of alpha xn minus alpha x should become less than epsilon after certain n. This is same as mod of alpha into mod of xn minus x. Correct. So if mod of xn minus x, this term, if I can show that this is less than epsilon by mod alpha, then the product will be less than epsilon. Okay. So this is exactly what we will use. The only concern we have is alpha shouldn't be 0, but anyway that case has been treated separately. So anyway we are in the setup where alpha is not equal to 0. So let me now write the formal proof. So given epsilon greater than 0, there exists n1 in n such that mod of xn minus x is less than epsilon by mod alpha for every n greater than or equal to n1. Correct? So we will make this difference as small as we want. So we will take epsilon as now epsilon by mod alpha. In the earlier case, we were taking epsilon as epsilon by 2. Okay. So now what do I have? I will simply use this same n because I don't have any other sequence in picture. So now I will write mod of alpha xn minus alpha x could be written as mod of alpha into mod of xn minus x, which is less than mod alpha into epsilon by mod alpha for every n greater than or equal to n1, and this is equal to epsilon. Therefore, we have found out n1 such that given epsilon greater than 0, there exists this n1, which is this same n1, such that mod of alpha xn minus alpha x is less than epsilon for every n greater than or equal to n1. Okay, so we have proved part C of this theorem. Now let me go to part B. Part B is about the product xn into yn. Okay, so what can I say about xn into yn? Let me try to again do some background calculations. I want to show xn into yn goes to xy. So I want xn yn minus xy. Correct. So what I know is I know something about xn minus x and I know something about yn minus y. So how do I bring in those terms? I will do x and yn minus, I can add and subtract x and y. Okay. And then I can have this. Okay. So Now, from these two terms, if I take xn common, then I'll be left with yn minus y. And from these two terms, if I take y common, then I'll be left with xn minus x. So that could, that would bring things into my comfort zone because I know something about xn minus x and yn minus y. So let me try to rearrange. So this I would write as xn into yn minus y plus this I would write as y common into xn minus x. Okay, so far let us just check the signs. I have minus x and y plus x and y. So if I take x n common, I have y n minus y. Then if I take plus y common, then I have x n minus x. Okay. This I can write by triangle inequality as less than or equal to mod xn into y n minus y plus mod y into xn minus x. Okay. Which is nothing but mod xn into y n minus y. This can be written as mod y into mod xn minus x. Okay. See, we have proved in the earlier lecture that every convergent sequence is bounded, and we know xn is a convergent sequence, so xn will be bounded, and hence we can have some upper bound for it. So let mod xn be less than c, that is c be that upper bound for every n. This c exists since xn is a convergent sequence. This c exists and is finite since xn is a convergent sequence. Okay, xn is a convergent sequence. Okay, now I will use this c later. Where would I use this? So just like in the earlier case, I would make mod yn minus y less than epsilon by c, so that epsilon by 2c, so that c would get cancelled and I will have this first term less than epsilon by 2. Now what to do with the second term? Of course, one obvious suggestion that would come to mind is making mod xn minus x less than epsilon by 2 mod y. Then mod y will get cancelled because y is constant, y doesn't depend on n. But there is a small problem in it. What is that problem? The problem is mod y could be 0 because in this case we are not assuming y non-zero. We are assuming y non-zero only when we have to deal with xn by yn. So in this case y could be 0. So what we will do is instead of uh, using epsilon by 2 etc. here, we will write one more step. So I will write mod xn yn minus xy, continuing from this step, is less than c, because mod xn is less than c, times yn minus y plus mod y is less than mod y plus 1, and then mod xn minus x stays as it is. Mod y is less than mod y plus 1, and mod y plus 1 will never be 0 because mod y cannot be negative. Okay, now my half job is done. Okay, so from this now I get an idea that this should be made less than epsilon by 2c. This should be made less than epsilon by 2 times mod y plus 1, and then I'll get what I want. Okay, but again this was background calculation. How would the textbook proof look like? Let me write the formal proof now. So given epsilon greater than 0, there exists n1 in n such that mod xn minus x can be made less than epsilon upon 2 times mod y plus 1. Okay, then with the same epsilon there exists n2 in n such that mod yn minus y can be made less than epsilon upon 2c. Why did we choose this specific form? Because of the background calculation over here. Okay, so now I will write the earlier thing. So now I know, so I will write those things. So x and yn minus xy we will write as x and yn minus x and y plus x and y minus xy. Then we will write all the in-between steps and we will finally get this less than c mod yn minus y plus mod y plus 1 into mod xn minus x. In between steps we have anyway written earlier, so you could copy those. And now if I choose n naught as maximum of n1 comma n2, then for every n larger than or equal to n naught, both these results will hold. Okay, for every n larger than or equal to n naught, this will also hold and this will also hold. So I will have this less than c into epsilon by 2c plus mod y plus 1 into epsilon upon 2 times mod y plus 1. One small technical detail. Here dividing by c doesn't change the sign because I know c is positive. Why c is positive? Because c is an upper bound, c is a bound for mod xn. Mod xn is positive. Okay. So this gives me epsilon by 2 plus epsilon by 2, that is epsilon. Hence we have proved that for every n greater than or equal to n naught, mod xn yn minus xy is less than epsilon. Okay. Hence we have proved that x and yn converges to xy. Now to prove the last result, what we will do, we will first prove that 1 by yn converges to 1 by y, and then we will use the result related to product. So first we will try to show that 1 by yn converges to 1 by y. How would I do that? Again, let us try to do some background calculations. So I could write this as y minus yn divided by y into yn. Okay. I know y minus yn has some bound, but what to do with this? Mod y into yn. So see, the thing is, now if I make this smaller, that is not going to really help me, because if I make denominator smaller, then the overall fraction is going to get bigger. I am interested in making the fraction smaller, so I should make denominator as large as possible. Can I make denominator large? Here is where we'll use the result that we proved yesterday. So yesterday we proved a result that if xn converges to x, then there exists n naught in n such that mod xn is greater than mod x by 2 for every n greater than or equal to n naught. Okay, so we will use that result. Now here what I'll say, yn converges to y, therefore there exists n1 in n such that mod yn is greater than mod y by 2 for every n greater than or equal to n naught. As a result, mod y into mod yn is greater than mod y whole square by 2 for every n greater than or equal to n naught. Mod y whole square is simply y square. Okay. And now here anyway I know y is non-zero, because only in this case we will be defining 1 by yn or 1 by y. So I could say that the denominator is larger, so I will write 1 upon mod y yn is smaller than 2 by mod y square. Is it okay? For every n greater than or equal to n naught. Okay. So if I make now mod yn minus y as less than epsilon by 2 times mod y whole square, then I think my job will be done. Okay. So let us try to write a formal proof now. Okay. How would the formal proof go? So given epsilon greater than 0, there exists n1 in n such that mod yn minus y is less than epsilon by 2 times y square. I don't have to write mod y square. Epsilon by 2 times y square for every n greater than or equal to n1. Similarly, for the same epsilon, there exists n2 in n such that mod yn is greater than mod y by 2 for every n greater than or equal to n2. This implies mod yn is greater than y square by 2 for every n greater than or equal to n2, which implies 1 upon mod yn is less than 2 by y square for every n greater than or equal to n2. Therefore, now 1 by yn minus 1 by y, which could be written as y minus yn upon yn, is same as mod y minus yn divided by mod yn. Okay, so this I can say is less than mod y minus yn upon y square for every n greater than or equal to, actually it is n2, but now what I'll do, I will again define n0 as maximum of n1 comma n2 because I have to use both these results, this result as well as this result. So for every n greater than or equal to n0 this happens, and mod y minus yn is less than epsilon y square by 2 again for every n greater than or equal to n0. So here we have used the fact. So in the first step I have used this fact that mod yn 1 by mod yn is less than 2 by y square. That is what we have used. And in the second step I have used the fact that mod y minus yn is less than this one, epsilon y square by 2. So I'll be left with just epsilon because 2 will get cancelled, y square will get cancelled, and hence we have proved that for every n greater than or equal to n0, mod of 1 by yn minus 1 by y is less than epsilon. Thus, what we have proved? Thus, we have proved that 1 by yn converges to 1 by y when yn is not equal to 0 and when y is not equal to 0. Okay. So we have now proved that 1 by yn goes to 1 by y. And now we can use this result along with the earlier result to prove that xn by yn goes to x by y, because I have xn going to x and I have yn going to y. If y and yn are non-zero, then this would imply 1 by yn goes to 1 by y, and then I'll use the multiplication thing, that is part b, which will give me xn into 1 by yn goes to x into 1 by y. Okay. Hence we have proved that if I have two convergent sequences xn and yn, then xn plus yn, xn into yn, xn by yn, provided it's well defined, and alpha xn, all these also become convergent sequences and we know their limits also. Okay, so let me stop here. Thank you.